Welcome to NET311, layered VPC security and inspection. Hope everyone is doing fine, getting settled into their first day at reInvent. My name is Pradeep Mankad. I'm a solutions architect specializing in networking. In the role, I work closely with customers, help them architect their network architectures on AWS and hybrid environments. And I'm joined by my colleague, Rashpal Clare.
Hello, everyone. Rashpal Clare, solutions architect based out of Milwaukee, Wisconsin. For those of you who don't know where Milwaukee is, it's a northern suburb of Illinois. That's a joke, by the way. I cover strategic accounts, so I cover some of the largest customers in AWS with the architectures around networking. So let's get going. So this is a 300-level session. We'll expect that you already have some good knowledge of IP routing, site annotations, DNS resolution, and IP subnetting. In this session, we'll be going over a breakdown of foundational constructs, a deep dive into network architecture so you know where to put your security constructs, and then we'll all round it up with a session on observability and orchestration, how to put them all together. In this session, we'll also be looking at how do we secure resources within a VPC in one region. We'll look at how do we secure resources within multiple VPCs in a region. What happens if we add a second region? How do we secure resources between regions? We all love the hybrid approach. How do we secure resources between on-premise, branch locations, data centers? We'll be looking at that as well. And at the end, we'll look at two very common architectures, the Ingress security and Egress security. With that said, let's get going and look at some of the services that we're looking at today. So we want to start by looking at resources that we can use or services we can use within a VPC, right? We want to look at security groups. We want to look at network ACLs or NACLs. Not here to start a war. Everyone has their own way of saying it. I'll stick to network ACLs. Next, we're going to look at the VPC boundary. Let's take a step outside of the VPC. We're going to look at a combination of the gateway load balancer with third-party appliances like firewalls. And we also want to look at the AWS network firewall. For application security, we want to be able to look at the AWS Web Application Firewall, the WAF. Observability, we want to look at flow logs, we want to look at traffic monitoring, so we have clear insight as to what's happening in our environment. And then orchestration, how do we put it all together in a method that scales across one VPC, one account, to thousands or hundreds of VPCs and accounts. Let's start with security groups. Any resource in your VPC that has an elastic network interface and ENI has to have a security group attached to it. Security groups by default are stateful. What that means is all traffic allowed in will also be allowed out. By default, nothing is allowed in, so everything is blocked. You specifically have to go in and add a rule to allow traffic in. What this means is you have to create a rule that allows IP and port. Now, with security groups, you can cross-reference them. What I mean by that is if you have two VPCs that appeared, VPC A and VPC B, you can reference a security group in VPC A over in VPC B. Now, this is only across VPC peers, not across transit gateways, so keep that in mind. Also, a handy little hint, prefix lists. We have all been through groups of addresses. We don't want to fill up our security groups with address lists. What we have released is prefix lists. You can create one prefix list of thousands or hundreds of addresses that you can assign to a security group. Really handy tip to make sure that if you have a standard group of addresses that you want to send across, you can reuse that prefix list as you send them across multiple VPCs. In a simple three-tier architecture, we want to break up security groups by tiers. So in this example, we have the web ELB tier. We have a security group for that. We also have a security group for our web servers and a security group for our database. Each different tier should only allow the tier above it. We don't want access that's unnecessary or wide open security group like a 0/0. That's really bad. Next, network access control lists. Network access control lists are stateless by design. What that means, you have to allow traffic in and traffic out. So if you allow port 22 in, you have to allow the ephemeral ports out as well. This becomes quite tedious to maintain. By default, we allow all traffic in and out. Network ACLs are surrounded by they secure our subnets. And what I mean by that is they will look at all traffic coming in and out of a subnet. If you route to a subnet, an ACL does not get evaluated at that point. A key note to keep in mind here as well, the rule evaluation handles from smallest number to largest number, right? So hint, if you're going to set up ACLs, Make sure that your numbers are 10, 20, 30, 40, or 100, 200, 300. So if you have to add or remove later on, you have the space to do so, right? So keep that in mind. Now, beyond security groups, let's look at a couple of things. Limits. By default, you get 60 security groups. You can scale that up to 1,000. Network ACLs get you to 20. You can scale it up to 40. Now, if you look at the depth of what can we do with security groups and how can we secure them, they look at layer 3 and layer 4, IP and port. Now, a really good hint is the AWS Firewall Manager service. If you have a specific security group that you want scaled to all your VPCs, use the AWS Firewall Manager service to then deploy this out to all your VPCs. So you have a standard group that can then be audited across all your VPCs. So like I mentioned earlier, this is a 300-level session, but I want to cover some fundamental constructs. Let's start with VPC routing. Every subnet has to have a route table associated with it. You can have specific route tables for specific function of that subnet. In this example, the top subnet, subnet 1, has a default route to the internet gateway. It's probably sending traffic out to the internet. Subnet 2 in the same VPC could have a default route that sends traffic to the transit gateway, a separate need altogether. You can have one route table associated with multiple subnets, but you have to have one subnet per route table. Next, ingress routing. In this example, we have an internet gateway. Now, there's a specific route table associated with the internet gateway, the ingress route table. This allows for more specific routing. In this example, if I want traffic from the internet coming in to get inspected by, say, an appliance or an ENI or a monitoring device in subnet 1, before it goes to subnet 2, I can have more specific routing. If you look at the route table, it says the 10.0.2.0/24 is routed to ENI X. That's the subnet for subnet 2. Now, all traffic will come in, hit ENI X, and then get routed down to subnet 2. Also keep in mind, all traffic has to flow back the same way it came from. If you look at subnet 2 route table, the default route goes back to ENI X. And then from ENI X, it goes to the IGW and back out to the internet. Now, early on, I was mentioning the local route. The local route is the route of the VPC side of the VPC. In this case, is the 10/16. In this example, I don't want any traffic going through subnet 1 to 2 before it gets inspected in subnet 3. That could be a monitoring device, a traffic mirroring device of some sort. We want to make sure that all traffic gets inspected before going there. Recently, we released more specific routing. You can have a more specific route in your subnet route table that is more specific than the local route. In this example, all traffic destined for subnet 2 has to be routed to ENI X, which lives in subnet 3. And then it follows the local route to subnet 2, I'm sorry. The return traffic will then use the route for subnet 1 that points to ENI X for symmetric routing, and then it follows the local route up to subnet 1 and to where it came from. Now keep in mind, you want to make sure that if you're using this example, think of what you're using that ENI for. If it's a firewall device, make sure that you can use other resources like security groups and NACLs, so you don't have something that just layer 3 and layer 4 inspection and filtering. Now, I've been talking about single VPCs. Now, nobody here has a single VPC in a single account. I see a hand raised, I hope not. So we all have multiple VPCs, multiple accounts. This is where the transit gateway comes in, right? This is your cloud router. This is where all your network connectivity resides. Think of it direct connect, your IPsec VPN tunnels, your SD-WAN appliances. This is where you can handle all your cloud routing in one centralized location. Now, a transit gateway is a distributed system. It's not one item or resource by itself. Early on in June this year, we released AWS Cloud WAN. This is our global platform or a central pane of glass for all our resources across multiple regions. If you have branch offices, data centers across the world, AWS environments, you can connect all of them with AWS Cloud WAN with segments and policies. So you have a very clean and distinct way of routing between all your regions and all your other destinations. What does that look like when it comes to routing? I like to think of this as, if you know my address, you can get to my house. If you can get to my house, you can do something malicious. If you can't route to me, you can't do something malicious. You don't know my address. So if you kind of look at it, in the AWS Transit Gateway, I have two prod VPCs that are attached to a prod route table. That prod route table only has a route to the shared services VPC. Same for dev. I'm segmenting my security by routing. In this scenario, prod and dev will never talk to each other. They can only talk to the shared VPC. Now, the same construct applies to Cloud WAN. The difference here is now you create segments across your regions. Your prod VPC is attached to a prod segment with its prod policies, dev, and your shared services as well across multiple regions. Now, another key construct to understand to be able to build the security principles is load balancing. Now, I'm going to introduce the AWS Certificate Manager, ACM. ACM allows you to generate public certificates to then be attached to the application load balancer, ALB, CloudFront, or API gateway. Now, with this, what's really cool about this is it auto-renews when the time comes to renew your cert. All the other services that are attached to the ACM will also get updated along with it. Now, the conundrum here is, if you have a third-party firewall that needs a certificate, you cannot export an ACM certificate. What do you do in this scenario? You generate a public certificate from an outside certificate manager, you then import it into ACM, and then you can attach that to your application load balancer or CloudFront, and then you manually attach that to your firewalls at that point. Another key thing to understand, target groups. Application load balancer has 3 main target groups. You can target an instance, an IP address, or a Lambda function. You cannot target an ALB to an ALB. That just does not function. The other construct to really understand is a full proxy versus a bump in the wire. Full proxy. So in the first scenario, user sends traffic to the application load balancer. That's one traffic flow. Then there's another traffic flow from the application load balancer to the target. The target will see the IP being the source of the application load balancer. Now, the bump in the wire, I'm going to introduce the gateway load balancer concept here. The user has traffic that's now routed to the gateway load balancer, right? The gateway load balancer would then send it to a firewall appliance to make an inspection, a filtering decision before it's sent to the target. Neither the user nor the target knows the traffic has been inspected. It's been routed through it and then to the destination. Now, I mentioned the gateway load balancer. This is a key construct for those who have third-party firewalls, load balancers, or even their own Linux appliances that run IP tables. You could have this, the gateway load balancer is a special type of load balancer that allows you to scale up and scale down as needed, and also manages the availability of your fleet behind it. So if you look at this example, there are 2 parts to it, the front end and the back. So in this example, the source is routed to the gateway load balancer endpoint in your VPC. It then hands the traffic over to the gateway load balancer, which then encapsulates it within a Geneve packet. Now this is just an extra header on top of the original packet, and then it's sent over to the firewalls. In this example, the firewalls understand Geneve, they're able to decapsulate the packet, make a decision, and then send it back from where it came from. So firewalls back to gateway load balancer, to the endpoint, and to the destination. Now, if you don't want to use third-party firewalls, you can use the AWS managed service called AWS Network Firewall. This is under the covers. It also uses gateway load balancer, and it also uses the Suricata, open source Suricata engine to do its IPS, IDS, and filtering. Now, with the network firewall, since it's fully managed, the scale up and scale down is managed by AWS. You're able to create policies based off IPS, IDS rules that Suricata provides. You can create IP rules. You can create rules that do web filtering if you decide to as well. Now I'm going to hand it over to Pratik to do the deployment models.
Thanks, Yashpal. So as we start architecting security inspection architectures to protect your network, it is important to understand where you implement your security components, the security endpoints into your architectures. And what I mean by that is basically, are you centralizing your security components into a centralized inspection VPC, so traffic is going into that centralized inspection VPC before it pans out to multiple VPCs? Or each VPC is having its own unique security stack and processing the traffic accordingly. So before we get started with the network architectures, I would like to spend some time going over these deployment models. So the first up is the distributed deployment model. So as we see in this diagram, each VPC has its own security inspection, security components. And what this means is like basically the blast radius is reduced here. And along with that, if you look at the cost component, basically you're directly reaching to your resources into your VPC. So basically, you're not traversing multiple components like transit gateway, so your data processing cost will be lower. At the same time, since each VPC is having its own unique security components, your per hour cost might be higher. Again, it really depends on the architecture, and these are some of the points that you need to keep in mind when you're designing your architecture. The next one is the centralized deployment model. So as you can see in this diagram, in the centralized deployment model, we have this dedicated inspection VPC where you're hosting your security solution. So your security components are centralized, they are centralized in the centralized inspection VPC. So all the traffic is routed to this centralized inspection VPC. Your firewall rules and policies are applied there, and then from there, they are being fanned out to different VPCs. So the thing to keep in mind is, like in this architecture, since the traffic is traversing multiple components, so traffic hits VPC 1, then it hits the transit gateway, then another VPC, and so on and so forth, you'll be incurring higher data processing cost. But since all your security components are centralized in one security VPC, you will be incurring lower per hour cost. Again, similar to distributed architecture, it really depends on the type of the architecture. But these are some of the points that you need to keep in mind while you are designing your architecture. And then what we have is a combined deployment model. So in this scenario, you might have a use case where you need to have a security components, security solutions deployed both in a centralized deployment model as well as in the distributed deployment model. And when it comes to deciding which deployment model to choose, so when you're doing east-west inspection, when you're inspecting traffic between the VPCs or between the VPCs and on-premises infrastructure, we recommend to use centralized deployment model. When it comes to internet egress or internet egress, there is no golden rule there. It really comes down to you as a user, which architecture better suits your needs, which architecture is easy to manage, and it really depends on what kind of solution you are using. So with that in mind, Rashpal went over the gateway load balancer construct and the network firewall construct. So I want to go over, spend 2 minutes on how they differ when it comes to the centralized deployment model and the distributed deployment model. So let's take a look at the distributed deployment model. So in case of gateway load balancer, you have a inspection VPC where you're hosting your third-party firewalls. They are added as a target behind a gateway load balancer. You have created a VPC endpoint service. And in the target VPC where you want to inspect the traffic, you created the gateway load balancer endpoint, which then routes traffic to the gateway load balancer and to the firewall for inspection. And when it basically in this scenario, the third-party firewall is either managed by the customer or it can be also managed by the service provider, meaning we have partners who are offering firewall as a service. So when it comes to AWS network firewall, so the inspection VPC is basically, we take care of that for you. So hence the name, manage AWS network firewall. So everything remains the same. So in the target VPC where you want to inspect the traffic, you still go ahead and create the firewall endpoint. But so it's part of the provisioning of the firewall. So when you start provisioning the firewall, you specify the subnet and it then creates the endpoint in those subnets. And that inspection VPC is all managed by us. So that network firewall is all managed by AWS. And one thing to keep in mind is while the network firewall is managed by us, the underlying infrastructure is managed by us, the configuration is still your responsibility. What sort of rules you want to apply, what sort of policies you want to apply is still your responsibility. And the firewall endpoint is still a gateway load balancer endpoint. So when you're deploying a third-party firewall or you're deploying a firewall, AWS managed firewall, the endpoint that is routing the traffic to either of those firewalls is still a VPC endpoint of type gateway load balancer. There's no difference between those two. And in case of, there's another subtle difference between the network firewall and the third-party firewall. So when you're in a distributed model, you can have one-to-many mappings. What I mean by that is you can have multiple VPCs pointing to the same firewall stack. But in case of AWS Network Firewall, it's a one-to-one mapping. So each VPC has its own firewall stack. But yeah, you can manage all these things through AWS Firewall Manager, so it doesn't, you don't need to worry about, oh, as the VPC increases, the size of the firewall management might be a challenge. And in case of centralized deployment model, so what changed here is, like, as you can see, the endpoint is also being instantiated in the same VPC as the firewalls. So basically, the firewall endpoint is in the same VPC as your third-party firewall. And you have this transit gateway subnet where you have associated the transit gateway with that, or it can be a Cloud WAN segment. And the similar concept applies for the network firewall. So nothing changes there. So in this scenario, you have a dedicated VPC where you have created the firewall endpoint to route the traffic to the firewall. So as we progress through the presentation, you'll see the firewall icon. So what it means, like, it can be either a AWS managed firewall or it can be a third-party firewall. It's basically transparent at that point. And then you'll see a gateway load balancer endpoint icon. It can be either, again, a gateway load balancer endpoint or a firewall endpoint. So the architecture kind of remains the same, either or for either of the firewall you pick and choose for your architecture. So let's get started with the network architectures. So what we are going to cover is, like, how do you inspect the traffic between the AWS environments? We'll take a look at the architectures that allows you to inspect traffic within the same VPC. We'll take a look at the architecture that allows you to inspect the traffic between the VPCs within the same region, between the VPCs across different regions, between the VPCs and your on-premises infrastructure, internet egress, and internet egress. So with that, let's start with the architecture that allows you to inspect the traffic within the VPC. So in this, what we have two instances that reside in app subnet 1 and app subnet 2, and you want to inspect the traffic between the two subnets. So in this scenario, we rely on the more specific routing that Raspal covered in the foundational construct. So you have those two subnets are associated with a route table. And you can see the local route has been, the target has been changed from local to the gateway load balancer endpoint. And that allows the traffic to be routed to the gateway load balancer endpoint for the inspection. So let's see how it works here. So let's say instance 1 wants to communicate with instance 2. It does a route table lookup, finds a entry matching, and sends it to the gateway load balancer endpoint. Gateway load balancer endpoint sends it to the firewall over AWS private link, gets inspected by the firewall. Assuming it is allowed, it sends back to the gateway load balancer endpoint subnet. At this point, it does a route table lookup again, finds a route matching to the local entry, and sends it to the destination. So this was within the same AZ, so it works fine, perfectly fine, not a problem. What happens when you do it, when you have subnets that are spread across multiple AZs? It becomes interesting, the multiple AZ scenarios become interesting because the endpoints are zonal in nature. So we need to keep that in mind. In order to maintain the asymmetric routing, we have to pick an endpoint between two AZs to inspect the traffic. So what I mean by that is, let's say if you want to inspect the traffic between AZ1 and AZ2, so in that scenario, I'm picking an endpoint in AZ1 to inspect all the traffic between the two AZs. Between AZ2 and AZ3, I'm picking an endpoint in AZ2 to inspect the traffic. And between AZ2 and AZ3, I'm picking the endpoint in AZ3 to inspect the traffic. And by doing this, what happens is, like, let's say for some situation, AZ1 is having some problems. In that scenario, only the traffic between AZ1 and AZ2 is affected, or the traffic between AZ1 and the corresponding AZ is affected, but AZ2 and AZ3 can keep working fine. So let's take a look at the packet flow, how it works. Again, similar to the single AZ scenario, when you want to inspect the traffic between the two AZs, AZ1 and AZ2, it does a route table lookup, finds an entry matching, it sends it to gateway load balancer endpoint 1, goes over to the firewall over AWS private link, gets inspected, comes back to the gateway load balancer endpoint subnet, does a route table lookup, sends it back to the instance 2. And this is how the traffic got inspected. And similar pattern is observed between AZ2 and AZ3 and AZ3 and AZ1. So that was between inspecting the traffic within the VPC, between the subnet. Let's take a look at the architecture where you want to inspect the traffic between the VPCs in the same region. So in order to inspect traffic between two VPCs in the same region or different regions, or between VPCs and on-premises infrastructure, as I mentioned earlier, you need to have the security components deployed in a centralized inspection VPC. And also, another thing to keep in mind that in order for this design to work, we need to have what Raspal just went over is a transit gateway. Again, transit gateway allows you to connect all these pieces together. And basically, the traffic between the two VPCs at this point is being routed. So if you look at this, so you have this spoke VPC route tables that has default route pointing to transit gateway. And transit gateway has, so the route table associated with the spoke VPC route table has a default route pointing to the inspection VPC. Transit gateway has another route table which is associated with inspection VPC, which has respective spoke VPC routes in it. And then on the inspection VPC side, we have transit gateway route tables associated with the transit gateway subnet. Again, we recommend that when you are associating VPCs with transit gateway, you have a dedicated subnet for those transit gateway attachments. So you can see that each route table has its default route pointing to the gateway load balancer endpoint in the same AZ. Again, this is to maintain the AZ symmetry. And so the route table associated with the endpoints, you'll have a summarized route pointing to transit gateway. So let's take a look at the packet flow here. So by default, let's say we have an instance 1 in AZ1, in spoke VPC1 wants to communicate with the instance 2 in AZ2 in spoke VPC2, and you want to inspect the traffic. So by default, it does a route table lookup, and it sends it to the transit gateway ENI in the same AZ, and then it sends it to the transit gateway. Transit gateway at this point does a route table lookup, and it finds a route pointing to the gateway load balance inspection VPC. And then again, by default, transit gateway always maintains the AZ affinity. So in this scenario, it sends it to the TGW ENI in AZ1 and sends it to the gateway load balancer endpoint for inspection, gets inspected, comes back, and it sends it to the transit gateway. Transit gateway does a route table lookup and sends it to the instance 2 in AZ2 in spoke VPC2. So in case of written packet, so it follows the similar path. It does a route table lookup, sends it to transit gateway 2. It maintains the AZ affinity, so it sends it to, at this point, transit gateway sends it to AZ2 ENI, and at this point, AZ2 will send it to gateway load balancer 2, gateway load balancer endpoint 2 in AZ2. And this gateway load balancer endpoint will send it to a firewall node in AZ2. And then the firewall says that I have no notion of this packet, I have not seen this packet before, I'm going to drop it. So basically, we introduce asymmetric routing here because the initiating traffic was processed by the firewall nodes in AZ1, but the written traffic got sent to the firewall nodes in AZ2. So they're like, I have not seen this packet, I'm going to drop it. So how do you solve that problem? So we have this feature called appliance mode. It is an attribute of VPC attachment. So when you enable that appliance mode on that VPC attachment, in this scenario, we are going to enable it on the security inspection VPC attachment. It makes the transit gateway AZ independent. So what happens is like transit gateway will pick the next hop for the life of the flow. So in this scenario, what will happen is like transit gate, the written packet comes back to transit gateway, and transit gateway is like, okay, this is, I've seen the initiating packet and I've already picked next hop for that, which is AZ1 in this scenario. And I'm going to send it to the same firewall again. Firewall at this point will allow it and send it to the transit gateway. So basically, it allows, the appliance mode allows you to maintain the symmetric routing in this scenario. And at this point, the packet is routed back to the source. So that was between the VPCs in the same region. What happens when you have VPCs across different regions? So similar concept applies, but there are two methods. So basically, you can do a single inspection where you can, similar to the AZ architecture, you can pick a region to inspect the traffic between the two regions. So that's what this architecture is about. So in this scenario, we have picked region 1 to be the region that will inspect the traffic between the two regions. And then we have route tables associated with transit gateway. So it has a default route pointing to the inspection VPC. We have another route table associated in region 1, which has a peering route. So we have a transit gateway peering, which is attached to the cross region. So it's sending packet to the other transit gateway in another region. And then what happens, let's take a look at the packet flow. It goes to the transit gateway. From transit gateway, it goes to the inspection VPC for inspection, comes back to the transit gateway, goes over the transit gateway peering, and transit gateway then sends it to the destination. The return packet follows the same path, goes to the transit gateway, gets inspected by the inspection, security inspection in the region 1 VPC, and sends it back to the source instance. The second option is like we have run across, like when I talk to the customers, they're like, yeah, this option works, but we have the policy where we want destination-based routing, so this really doesn't work for us. So in this scenario, what happens is like you will go with a double inspection architecture. And so each region has its own inspection stack. Each region is considered as a secured region. So any traffic coming into that region is being inspected by that security inspection appliances sitting in that region. So similar to the previous architecture, you'll have transit gateways basically having default route pointing to the inspection architectures. And then you also have a transit gateway pointing to each other to the peering attachment route. So that's the changes you see in the route table. So again, based on the routing, you're routing the traffic either to the inspection or directly to the resources. If you look at the packet flow, it goes to the transit gateway, goes to the inspection VPC, back to transit gateway, or to the peering attachment to another transit gateway, gets inspected by the inspection VPC in the other region, and then sends it to the destination. The written part follows the same thing, goes to the transit gateway, gets inspected by the security appliances in the same region, to the peering, gets inspected again, and back to the source in the region 1. So that was about the VPCs across the same, across the different regions. So now the other use cases, like you want to inspect the traffic between the VPCs and your on-premises infrastructure, how do you do that? So similar concept applies here. So you have, in order to, you might use a VPN. In this diagram, I'm showing AWS Direct Connect, but you might also have a VPN to connect your branch office. But you have a transit gateway that enables the connectivity between your on-premises infrastructure and the VPC. You have a centralized inspection VPC where you're hosting your security solutions. And then similar to the route table, nothing changes there. It's basically those route tables pointing to the gateway load balancer endpoints. And then you have gateway load balancer endpoint route tables that is pointing to the transit gateway. So, and then you have a default route pointing to the inspection VPC attachment. So when the packet arrives from the VPC to the on-premises infrastructure, it goes to the transit gateway. It goes to the inspection VPC, back to transit gateway, direct connect gateway, direct connect, and on-premises. And the written path follows the same path, direct connect gateway, transit gateway, inspection, and back to the source subnet. So that was about how do you inspect the traffic within the AWS environment. Now let's take a look at Ingress inspection architectures as well as the Egress inspection architectures.
Let's have a look at the microphone, and let's look at Ingress architecture. So should I centralize my internet egress or should I not? There are pros and cons to the solution here. Let's look at this. So in a lot of my customers, they have a central team that manages all ingress. Either a security team, a network team that says, all my ingresses are coming through one central point. I'll manage, control, operate it, and do all kinds of maintenance on it. That's one way of doing it. They also don't want a proliferation of IGWs in all VPCs, right? So they go, let's just centralize it. It's an easy way for us to do it. Let's keep it this way. What's the cons of doing that? Blast radius, for obvious reasons. You put all your eggs in one basket. If you have one ALB with multiple paths, multiple certs, right? You're one change away from disaster. Don't do that to yourself, right? It also adds complexity and cost. What I mean by that is if you put all your resources in one VPC, the resources that they need to hit are probably going to be in a different VPC in a different account. So now you're routing, right? You're adding complexity. You don't want to call at 3 in the morning, my ALB doesn't work, my resources aren't getting traffic, what's happening here, right? It adds complexity in routing in that sense. So I'm going to introduce the AWS Web Application Firewall. This is a layer 7 firewall. So think of your OS top 10 list. You can have IP sets in here. You can do reputation lists, and it's easy to attach to ALBs, CloudFronts, API gateway. Great solution for this. So let's look at a distributed model and how we would attach a WAF in a distributed model. So in this example, I have an internet gateway that receives traffic from the internet. I have an application load balancer in a public subnet, so it has a public IP address, and I attach the AWS WAF to it. A packet comes in, it gets decrypted on the application load balancer so that the WAF can do its filtration and inspection. Once it's done and it's allowed, it'll then be sent down to the EC2 instance in the back. This works for all traffic that's HTTP and HTTPS. Decryption is true if you use ACM. Now, the management is also centralized through Firewall Manager, so it makes it easy for you to then take this model and then copy and create multiples of those in other VPCs as well. What if I have CloudFront? So in this example, I'm going to attach the AWS WAF to CloudFront, put my security policies on CloudFront. Now, you may also see there's a WAF attached to the ALB below. The reason for that is we only want to allow access from the AWS CloudFront distribution from above. I don't want any other source sending traffic down. I'm going to lock that down as well. In a centralized model, let's introduce transit gateway. So similar to what Pratik mentioned earlier, the model is going to be very similar here. So I'm going to explain this through. So you have an inspection VPC that has all traffic coming in. Traffic's going to come in, hits the ALB that has WAF, it does inspection. Now, if you notice, in the application VPC, there's an NLB there. And I said earlier, you can't point an LB to another LB. So in this case, I'm pointing it to an NLB because it is a static IP address. So therefore, I can point my ALB to a static IP address and then route traffic through the transit gateway. Another example of this is to use private link. Private link has two parts. There's the endpoint, where the services come into, and then the network load balancer that sprays traffic across. Now, this is a one-way traffic flow. It goes from the endpoint to the NLB to the resource. No traffic can go the other way across. So if you look at the architecture, traffic comes in through the ALB, gets inspected by the WAF, sends traffic down to the interface, which is an IP address, which can be used by ALB, and then down to the application VPC. As such. In a distributed model, again, I'm going to have that Ingress route table that I mentioned that gets me more specific routing. In this example, I have two availability zones, AZ1 and AZ2. And here, the route table lookup will have the public subnet will point to the gateway load balancer endpoint in that subnet, and vice versa for availability zone 2. A packet will come in, the internet gateway, route table lookup will happen. It will send it to the gateway load balancer endpoint. It will then send it to the firewall for inspection. If allowed, it'll send it back. Route table lookup will happen again. I'll say I need to go down to a load balancer, hits the load balancer, and then from the load balancer, it then routes it down to target point. Packet flow as such. In this example, because the gateway load balancer endpoint is fronting the resources coming in, I can have any service coming through. It doesn't have to just be 80 in 443, HTTP or HTTPS. But in this scenario, I'm dependent on the functionality of the third-party firewalls, right? So if you have to do decryption, make sure you have an external cert attached to it. For management, Palo Alto has a really good solution, one of our partners in Panorama. You can essentially manage all your rules through that. In a distributed model, now in this case, I'm going to front my external traffic from the internet with a public-facing ALB or NLB first. In this scenario, I'm only going to allow traffic that I want to allow in. In this case, HTTP or HTTPS. So all other traffic that is just erroneous on the internet will never get past the load balancer because we'll drop it. In this example, the packet comes in. In this example, if you notice, I'm not using more specific routing. It's just regular routing. Packet comes in, hits the load balancer then sends a route to the gateway load balancer endpoint, to the firewall, makes a decision for inspection, sends it back, and then down to the target. And the traffic flow looks something like that. So ingress routing versus more specific routing. Which do I pick and why? If you look at ingress routing, the firewall will see all traffic, whether it's just the traffic you want to see or whatever is on the internet just spraying, trying to look out for stuff. You'll see all traffic. Now, if you so happen to get DDoSed, right, you're also responsible for scaling the firewall up and down because it will see all traffic. It will also help you to see the client IP address because it's the front end for all traffic coming in. So you'll see the public IP address of the client coming in. Now, if you want to use certificates, make sure you have a public certificate because you can't use ACM in this model because you can't export a cert from ACM. More specific routing. In this case, we front public access within the load balancer. In this case, we will only allow 80 and 443 through. Now, the firewall of the backend will see the source IP address coming from the load balancer. Now, if you want to see the client IP address, please add the X-forwarded4 option in the ALB. That will send that in the header down to the firewall, and then you can see it there as well. In a centralized model for ingress routing, if you want to have all inspection come in and then have the firewall make a decision before it hits the load balancer, this is what it looks like. A packet comes in from the internet gateway, hits the endpoint sends it to a firewall for filtering, if allowed, sends it to the ALB, and if you notice again, it's an ALB because it's a static IP address, it sends it down. Again, common theme with private link, same functionality. Packet comes in, endpoint, firewall, load balancer, and then through private link to get down to your application VPC at that point. In a centralized model for more specific routing, this scenario, I want the ALB or NLB to front the traffic coming in before it hits the gateway load balancer endpoint and firewall. Packet comes in, makes a route decision, load balancer, endpoint. Now, at this point, I have to route. It hits the transit gateway makes a decision, sends it to the application VPC where the destination is, where the NLB lives for the static IP address. Again, very common model, same for private link, where ALB is first, and then the gateway load balancer endpoint, private link, and then down to the application VPC. Another example that I want to call out is the ELB sandwich. It's load balancer, bread, firewalls, meat, vegetables, depending on what you like, and then bread again is an internal-facing load balancer. Packet comes in, hits the internet-facing load balancer. Again, with this, you can, depending on what certs you have, if it's a public cert, you can then attach the public cert to the internet-facing load balancer. Traffic is then sent there. You can decrypt, make a decision, send it encrypted down to the third-party firewall that you've uploaded a cert to again, and then send it down to an internal-facing load balancer before it hits its instance. Now, if you notice third-party firewall is involved here, all management is dependent on what the provider can give you at that point. In a centralized model with an ELB sandwich, it's internet gateway, load balancer, third-party firewall, route through the transit gateway, NLB, and into the system. And then a common method again, private link, ALB, third-party firewall, private link endpoint, and then to the NLB to the system in the back end. So let's look at what the IP packet actually looks like in an ELB sandwich. The user sends a packet, so the source is the user. The destination will be the public-facing IP address of the ALB. ALB gets it. What happens then? It does full proxy. Source gets changed from the internet-facing ALB's address down to the destination being the third-party firewall. Firewall does a SNAT as well. It then changes the IP address of the source to itself. The destination becomes the internal ELB. And then what does the instance finally see? The source being the internal ELB's address and the destination being itself. What does this look like if I had gateway load balancer involved? So IP packet from a user, looks familiar, right? User has a source, destination is the public address of the load balancer. Now, in this case, because I'm routing traffic to the gateway load balancer endpoint, and it's the bump in the wire, it gets routed to the gateway load balancer endpoint to a firewall to the destination of the instance, right? At this point, neither the user nor the instance or the container knows that it has been filtered, but it sends the packet through. What does this look like in a cloud WAN scenario? In a cloud WAN scenario, all we're adding in here is the global core network. A packet comes in to the ALB, here's the gateway load balancer through a route decision, and then we send it to a CNE, a core network edge ENI. This is specific to just the Cloud Run environment. It then makes a decision. It says, I have to route this back to the core network where the policies are held. It sends it to the core network where it's the shared environment. Shared environment looks at the policy statement and the route tables. It goes, I know where to send you once it's allowed. It sends it to the application VPC where there's another CNE interface there, sends it to the NLB with the static IP address, and down to the instance. The traffic flow looks something like this. Egress architectures. Everyone needs access to the internet. Whether you're pulling patches, calling an external API, this is a common use case across all customers, no matter how big or small, right? You can do what basic customers started off doing. You could surround a public subnet with a network ACL. Now, I was nodding the head or shaking the head. I don't want to maintain IP addresses of specific addresses. You're in the cloud, things are dynamic, addresses change all the time. This is going to be a pain, so don't do that. What we've seen customers do is use open source solutions like the Squid proxy to then forward all traffic to a Squid proxy. Squid proxy lives in a public subnet. It does all the filtering for you. And then once the filtering is done, it can then be sent out to the internet from there. Return traffic comes back the same way from which it came from. Internet gateway, egress proxy, down to the instance. Now with this model, customers are all responsible for all configuration, maintenance of any EC2 instances they have, so keep that in mind as well. In a distributed model, how do we get egress? Source needs to send something to example.com. Looks up a DNS entry, default route says, go to the NAT gateway. NAT gateway will then NAT the packet for the source address to make it a public address. NAT gateway does a route table lookup to say, I need to send this to the gateway load balancer endpoint for inspection, sends it to the firewall for inspection, sends it back if it's allowed. Since it already has a public address and already has been NATed, sends it off to the internet. Return packet. Again, that Ingress route table is key here to make sure that you route back to the proper AZ and the proper endpoint from which it came from. Packet comes in, comes back from the gateway load balancer endpoint from which it came from, goes back to the firewall for fully synchronous traffic flows, back to the gateway load balancer endpoint, NAT gateway, and back to the source from which it came from. Traffic flow looks something like that. In this example, all flows are supported because you're using the gateway load balancer endpoint with a firewall, a third-party firewall. It doesn't just have to be 80 or 443. Again, if you're using a vendor tool, management is dependent on what they have at that point. The functionality is dependent on what they have. In a distributed model, in this case, I want to make a decision before I even NAT anything, right? Depending on what your security posture is, this might be a solution for you. So in this scenario, source is going to send a route to the gateway load balancer endpoint. It's going to send it to the firewall, make a decision, are you allowed to get to the internet or not? If you are, back to the gateway load balancer endpoint, then to the NAT gateway for NATing, and then out to the internet. On your way back in, you don't need that specific Ingress route table because you're NATing it back, you're routing traffic back to the NAT gateway, and then to the gateway load balancer endpoint, back to the firewall for fully synchronous traffic flows, and then back to the source from which it came from. And it looks something like that. In a centralized model, as I mentioned, no one just has one VPCs, 100 VPCs in a region. You can have an app VPCs that says, my default route 0/0, send it to the transit gateway. Transit gateway will then have a route table that says, all zero traffic has to go to an inspection VPC. In here, it'll send it to the inspection VPC that has a TGW ENI, sends it to a NAT gateway to an inspection, which is the gateway load balancer endpoint. It makes a decision on whether it's allowed out or not, and then sends it out. Back it back in. Again, the Ingress route table, so it goes back to the right gateway load balancer endpoint. It gets back in, and the traffic flow looks something like this. This is a very common architecture to consolidate all your different egress points to one central egress VPC. In a centralized model, now if I flip it over, in this case, I want to make a decision before I NAT it. Same as I mentioned before. Packet hits the transit gateway to the ENI, hits the gateway load balancer to make a filtering and inspection decision, then it routes it, if it's allowed, to the NAT gateway to make a NATing decision, and then out to the internet. The way back in, it'll get routed back to the NAT gateway and then back down. Again, let's compare and contrast. In the Ingress routing model, the firewalls will only see the netted address of the NAT gateway. It won't see the actual source address of what it was in your VPC that actually made the request. On the more specific routing model, the firewall sees everything because it makes a decision first before it nets it. So depending on what your security constructs are, this one of these two solutions will function for you. Now again, with Cloud WAN, how does this function in Cloud WAN? As you can see, the common theme here of the segments and the policies attached to it, you have your application VPC. It'll make a routing decision to send it to the prod segment, because this is a prod VPC. It'll make a decision based off policy. It says, I want to get to the internet, send it to the inspection VPC. It'll then hit the CNE ENI there in that inspection VPC, route it to gateway load balancer, make a filtering decision, an inspection decision, NAT gateway, and then out to the IGW. And it looks like that. Now, another construct that we want to add on top of layering just common network security principles, right? The DNS firewall. Everyone's very familiar with the second address in a VPC being the DNS resolver for a VPC. In this example, what we do is when a DNS decision is made, we look up a private hosted zone first. Then we look up to see whether there are any AWS managed zones that we need to look up. And third, we look up to see whether it's a public zone that needs to be looked up. For example, if I'm looking at example.com, what's the DNS entry for that? You can have DNS firewall do that for you and have a filtering, a rule group, and allowed and denied domains for what, depending on what your security policy is, for only domains that you allow. So if I'm only allowing example.com or api.example.com to be resolved, all other resolutions should fail, I can do this as well. So if you think of a layered approach, I can have DNS security before I even route traffic to make a decision on whether it's allowed or disallowed. And if it is allowed, then I can route traffic to the firewall endpoint, and then to the NAT gateway, and then out to the internet.
Thank you, Rashpal. So I think we are in the home stretch of our presentation. So earlier when we talked about the deployment models, I focused on the data plane, we are focusing on the data plane side of the things. In this section, we'll also look at how you can manage, control your firewall policies and rules from a centralized single pane of glass. Along with the orchestration, we'll also look at various tools to monitor the traffic within your Amazon Virtual Private Cloud, aka VPC. So AWS Firewall Manager is a security management service that allows you to centrally configure and manage your firewall rules and policies across your AWS accounts and application. As applications are created, AWS Firewall Manager makes it easier to bring those applications and resources within compliance by applying the same set of security policies to those applications and resources. And when you're using AWS Firewall Manager, you need to be a part of, your account needs to be a part of an AWS organization, which is a service to manage AWS accounts with the AWS organization. You also need to enable AWS config. It's a service that tracks any changes in your AWS environment. And when you're managing network firewall and DNS firewall, you also need to share with your AWS organization using AWS Resource Access Manager, which is again a service that allows you to share your resources securely across your accounts, within your organizations or organizational units. And then last thing that you need to have is an admin account that allows you to manage things within your firewall manager. And Firewall Manager supports Web Application Firewall, Shield Advanced, which is a DDoS protection service, VPC security groups, AWS Network Firewall, Route 53 Resolver DNS Firewall, and it can also send a notification to Security Hub, which is again a cloud security posture management services that ensures security best practices checks and aggregates alerts and allows you to do those things. So let's see how it happens, right, with Firewall Manager. We have multiple VPCs here. We have 4 VPCs in 4 different accounts, and each of these VPCs is having an internet-facing application. And you want to deploy firewall in each of these VPCs. You can do that centrally using Firewall Manager. You basically choose the policy type and region. You go ahead and describe the policy. You describe the policy there. You then go ahead and select the endpoint type. You go ahead and configure the route management. You then define the policy scope. And then at this point, you define the policy tag. And then review it, apply it. And what it does is it just creates all the endpoints and the firewall in those each accounts. The only thing that left is here is you have to manually go ahead and edit the VPC route tables to make the route table changes. So that's the only thing that is pending here for you to do it. The next thing that we should be looking at is the flow logs. So we have a VPC flow log that allows you to capture information about the IP traffic flowing between the network interfaces. And you can basically create flow logs for elastic network interface, subnet, and or a VPC. When you're creating a flow log for a subnet and or a VPC, all the network interfaces inside those VPCs are monitored. And as far as the destination goes, the flow logs can be sent to Amazon CloudWatch, Amazon S3, Amazon Kinesis Data Firehose. And you can use the flow logs, VPC flow logs, to analyze the overly restrictive security rule groups, monitor the traffic that is reaching your instance, determine the directionality of the traffic coming in and going out of the network interface. So when you have multiple VPCs connected through transit gateway, in that scenario, you have to rely on the VPC flow logs of those VPCs. And it becomes really difficult, especially when the transit gateway owner doesn't have the visibility or access to the VPC flow logs. So earlier this year, we released a feature called Transit Gateway Flow Logs. This allows you to get the visibility of all the IP traffic flowing through Transit Gateway, and in turn allow you to access the VPC, like get the entire picture of the entire network architecture. So here are the flow log fields for VPC flow log. That is for default format and the custom format. And this is for the Transit Gateway flow log fields for the default and the custom format. Then we have VPC traffic mirroring. This is basically, the flow log is basically like a net flow. VPC traffic mirroring is like similar to your network tab, your port mirroring. So it's basically capturing entire packet. So basically it's capturing a packet from an instance, ENI, Elastic Network Interface, associated with an instance, and sending it to a target, which can be, again, an Elastic Network Interface associated with an EC2 instance or a network load balancer or a gateway load balancer endpoint. Next up we have is VPC Reachability Analyzer. It's a configuration analysis tool that allows you to check the connectivity between the source and the destination. So when source is able to reach the destination, the reachability analyzer lays down all the hop-by-hop details between the path. And if it cannot reach the destination, it also lets you know what is the bottleneck. So whether the destination is blocked by a misconfiguration in a security group or a route table or a network ACL or a load balancer. And you can use Reachability Analyzer to troubleshoot connectivity issues. You can verify the intended connectivity, whether your network configuration is allowing you to reach your intended connectivity, and also automate the verification of the connectivity intent. And here are the types of resource types that you can either use as a source or as a destination. And the last one on the list is the VPC Network Access Analyzer. So basically, this is a tool that allows you to understand the network access to your resources. It is important to understand what sort of architecture is required to protect your network. That being said, it is equally important to make sure that the architecture that you have architected is it's actually fulfilling your intent, it is fulfilling your business objective. So VPC Network Access Analyzer allows you to do that. And here are some of the use cases that Access Analyzers allows you to fulfill. It allows you to internet accessibility to resources in your VPC. It allows you to trusted network path, so you can check whether the network firewall or net gateway is there between the resources and the internet gateway. Network segmentation. It can allow you to do trusted network access, and it can also allow you to do private network connectivity. So that was about it. Thank you very much for coming to our sessions. Hope you had fun while you had learned something new. So thanks again, and please fill out the surveys.